So, the objective of this workshop is to provide everyone a venue for novel research in omnidirectional computer vision with an eye toward actualizing these ideas from commercial or social benefit. As omnidirectional cameras become more widespread, we want to bridge the gap between the research and application of omnidirectional vision technologies. Omnidirectional cameras are already widespread in a number of applications such as automotive, surveillance, photography, simulation, and other use cases that benefit from large field of view. More recently, they have garnered interest for use in virtual and augmented reality. We want to encourage the development of new models that natively operate on omnidirectional imagery, as well as close the performance gap between perspective image and omnidirectional model. So the main motivation for this workshop came from the immersive experiences to autonomous driving and medical imaging and so much more. We are increasingly seeing that maximizing a camera's field of view can solve real world problems. In the past few years, omnidirectional imaging has grown in interest and driven in part by the desire to maximize the amount of content and context encapsulated by a single image. Fisheye cameras installed in modern vehicles and commodity omnidirectional cameras from companies like Ricoh and Insta360 have helped to increase the popularity of this imaging modality and have opened the door for more consumer facing applications in the automotive, home services, uh, and real estate industries. Our workshop seeks to provide a link between the formative research that support these advances and the realization of commercial products that leverage this technology. We want to encourage the development of new algorithms and application for this imaging modality that will continue to drive this engine of progress. Having said that, we have two sponsors for this workshop, Qualcomm and Spleen Lab. And Spleen Lab has also arranged one of the challenges about which we would cover towards the end of the workshop. Having said that, we have two keynote speakers today, and I would like to welcome Jan Erik by telling something about his work. He is a distinguished luminary in the domains of technology and mapping, is set to grace our event as a confirmed speaker. Currently, he holds the prestigious position of chairman at Overture Maps Foundation and engineering director at Meta, showcasing his exceptional expertise and leadership. With a notable track record as the director of Maps at Meta and as a co-founder and CEO of Mapillary, Jan Erik has been a trailblazer in leveraging crowdsourced street-level imagery for mapping solutions. His past role as a manager at Apple, where he led the computer vision team and conducted pioneering research, further highlights his impactful career. As academic stalwart, Jan Erik's contribution as an associate professor at Lund University underscore his depth knowledge. Recognized twice as a WEF technology pioneer and armed with a plethora of 20 plus patents, along with being an acclaimed author. He is trying to offer profound insights and expertise to our audience, and I would like to welcome him for his talk today. I know. And so we go in the presentation mode and then do your screen and just get your slideshow.
Great. Thank you. Good morning, everyone. Right. Yeah, let's get started. It's quite an introduction. All right. I was going to talk a little bit about crowdsourcing imagery, street level imagery to be precise, for the purpose of mapping, but then also talk a little bit about what types of data sets you can create using imagery like this, and also show some research results that we have produced based on those images. Okay. First, need to give credit. So here's a group of people that work on the various community activities around Mapillary, around the apps, around the website, the backend. A lot of the work that I will show today is made by these people. And then a lot of the research results that I showed today, also from the research group here. So I'm not taking credit for any of the specifics in the talk today. All right, let's start with an introduction. How many in the room are familiar with Mapillary? Oh, wow. Okay, so let's dive into to the introduction. Okay, so Mapillary is a platform with apps and tools for crowdsourcing street level imagery, like the sequence you see here. So people go out in the world, wherever they are, and capture images in sequences. So you can do this as videos, you can do it as a sequence of still images. If you use the smartphone apps, the app will automatically take pictures at the right intervals to get the right coverage you want. So you could think of it as a way of crowdsourcing Street View for the places of the world where mapping vans don't drive on a regular basis. But then there's also the side where it integrates into mapping tools. So all of the major mapping platforms and all of the major map databases, including the one that I'm a chairman for, Overture, use this type of data to improve maps, and which is one of the main drivers behind people contributing imagery to the platform. So today there are about 2.3 billion images. The green, this is a screenshot from the website. Green is our color, so green shows where we have image coverage. And these images are, of course, geotagged. They're, of course, positioned with structure for motion, so you have pose. They are also indexed, so all of the content in the image has been labeled, and you can search for it. So, and then the tools then downstream from this integrate this into different mapping workflows. And so the idea that started it all, it's now over 10 years ago we started, was that instead of equipping vehicles, spending lots of money, managing a fleet, figuring out how to get coverage, you could just utilize whatever people have in their pockets or whatever they have available where they are. So if you turn on any camera, and so the main categories actually are smartphones, action cameras, dash cameras, and various forms of 360 cameras. But there are all sorts of strange constellations, and I will show some examples of that too. if you just let people capture with whatever they have, in whatever way makes sense to them, then we can try to make sense of that on the cloud side and turn that into something useful. But by doing it this way, you get ultimate reach. So as you saw on that coverage map, we have mapped many, many parts of the world that are not available on the big commercial platforms. And so these are typical ways of capturing, and I would say using the phone app, and the two main ones are the walking and the upper corner. So you just take your phone out when you see something interesting, or when you're on a street that hasn't been mapped before or had some recent changes, and you walk around with your phone. The second most common is to put the phone as the person driving down there in the front window of your car. And then you start recording and you drive, you do whatever you want. And then when you're done, the app will upload the images. All right. So based on all of these images from all of the users across time, across the various cameras that had contributed, we run structure for motion, we reconstruct all the areas, create point clouds, run semantics, we get a semantic 3D reconstruction, and then from this reconstruction, we then mine it to create map data. So the first thing that we turned on was traffic sign recognition. So as you can see, all of this stuff is visible on the website, so you can just go and explore it yourself. But you can see in this image that some of the signs have been highlighted in the image. You can see them on the map where they've been geo-positioned by triangulation. And then you can sort of browse around on the map, and this data is available through APIs. So if you're, let's say you're a ride-sharing company and you care about routing from A to B and turn restrictions and like what directions you're allowed to drive is important to you, you can go in, you can filter for turn restriction signs, and then download that data, or maybe even with APIs, hook it directly into your map editing workflow. So this is like running in about 100 different countries. Traffic signs vary a little bit over geography. And then we recognize other types of objects like poles and traffic lights and potholes, but that's not what I was thinking. Manholes, like the covers to the sewer system, crosswalks and sidewalks and things like that. And those are also available to filter and use. And then, like I mentioned, we also index all the images with segmentation. So you can find images that contain an animal crossing the road and a bike lane on the right side if you wanted to. So you can query based on image content when you're accessing the data set. All right, I'm gonna quickly go get my water. Okay, so let me show you a couple of examples of what this looks like. Well, actually, I wanted to show the first image. 2013, this was the first image uploaded to the Mapillary platform, and today 2.3 billion. All right, so a lot of the content that comes to Mapillary comes from various communities, and they're driven by different things. Like this is the Missing Maps community, which is trying to cover missing parts of the world, usually in developing countries. It could be cycling activist groups. It could be various interest groups around the world. They will then organize meetups like this one here. Sometimes if we know about it, we can help them. We can send them some instructions. We can send them some t-shirts. But they meet up on a regular basis and they go out and map. And one of the things we noticed was that early on is that they create these ad hoc rigs. It's very typical that each person will take their phone and they will designate different directions. So I'll take forward facing, you take like the slightly to the right, you take slightly to the left, this person takes full right, other person takes back, and then they walk as a crowd and create this ad hoc, completely uncalibrated, messy rig solution. But it actually works. You get really good results out of it and lots of useful map data. Here's a student group, I think in Italy doing mapping. Here's the Japanese community that actually organize real conferences on a regular basis, where they go out and map and improve the maps of Japan. All right. And then, of course, people started putting cameras on cars. This was the first user that we know about that did this. And this was before the action cameras had GPS, so you had to write tooling for geotagging them. Teslas. It's not great, but it works. I mean, the cameras are pretty close to the ground, so you don't get like a great angle. The color balance is not beautiful, but actually you can get access to the full range of cameras on your Tesla and then geotag it and upload it to Mapillary if you want. So here's an example of that. The Red Cross was actually very active in mapping the developing world by putting, in this case, it's a Sony action camera that has a GPS in the front window and driving around, had a huge contribution to the growth of maps in certain parts of the world. And then at some point, the dashcam manufacturer partnered with us and made a dedicated dashcam. This is that one. And with the help of this dashcam, this very dedicated user, the green traces here, that's his collection. So he mapped almost all of Australia by himself. This is his van. He drives around, he lives in his van, and he uploads with this dash cam continuously to Mapillary. Impressive. Yeah, and then you have all sorts of like when you go back to the initial premise of any camera, any combination of cameras anywhere, people start putting whatever they have on. So like I mentioned, action cameras with suction cup mounts on vehicles is pretty common. Sometimes they'll put a 360 camera on the top of the car and put some action cameras on the sides, depending on what this person is after. So, for example, people mapping points of interest and businesses and stuff like that, they care about the facades of buildings, so they'll have a side-facing camera and then maybe a 360. In Southeast Asia, most of the mapping that's sort of organized is done by 360 cameras on helmets, people driving motorcycles. But it's like completely uncontrolled, but great data for mapping. Here's another example. Selfie sticks are pretty common to get the camera up. So this guy put selfie stick on the side of his car. Selfie sticks on bikes, pretty common. This guy built an ad hoc rig with, I think this is in France, maybe. And this guy put a bunch of action cameras on top of a thing on his back and created an ad hoc do-it-yourself camera rig. It's pretty cool. And then, yeah, selfie sticks with 360 cameras and the pole stuck into your backpack is pretty common. Simple construction. You can like compact it and put the camera and the pole back in the backpack when you're done. And then some creative people started putting the backpacks in the rental bicycles and then bike around the city. Seemed like a more efficient solution. Anyway, you get the picture. All sorts of interesting combinations. And then sometimes people have access to more professional grade. This is a Trimble camera that the mapping community in Dar es Salaam borrowed from Trimble, put on a car, or I'll call it a car, I don't know the word. And they drove around and mapped the whole city. And then the images on the left is before and on the right after. So you can sort of see the level of detail that was added to the map by this group of people going out collecting imagery. Unfortunately, they crashed into a bridge and destroyed the camera they borrowed. But it's a good story still. Amazing work by this group. Yeah, here's Jeff from Mosaic. There are lots of images on Mapillary with the Mosaic camera. Great professional grade stuff. Here's the city of Detroit. They decided to. Typically, cities will hire these vendors, which I'm sure you're aware of. they go out and they capture with a van similar to this one, and then it costs a few $1,000,000, at least in the US. But usually you don't even get access, you don't even get full rights to the images, right? So Detroit said, okay, screw all of that, we're just going to do it ourselves. So they put some cameras on basically the same type of equipment, but on one of their own cars. And they started uploading it to Mapillary, became a very nice collaboration, which eventually turned into one of our best data sets, which is what I will show later. All right, so that was the Mapillary crash course. You can go to the website and click around and figure out yourself. But basically, lots of variety. We have everything, every single type of smartphone you can think of, every single 360 camera on the market, all the way up to the various professional grade equipments. Often several cameras capturing at the same time, unsynchronized, of course, but like a 360 cam and a phone, it's a very common combination. And so lots of ad hoc things, never calibrated, very interesting and challenging. Yeah, but you also get amazing coverage. Okay, so let's shift gears a little bit and talk about some of the data sets that we created from this corpus of imagery. I mean, anyone, including you guys, the images are Creative Commons licensed, so you can go into the website, figure out what you want, and take those images and build your own data set if you want. And there was actually someone that did that recently to create like a 5 million image data set for location recognition. I should have looked that up and put that in the presentation, but you can do that too. But here are some of the data sets that we created ourselves. And so if you go to mapillary.com/datasets, you can browse them there. And I was going to talk about 3 of them in this presentation. Okay, so the first one, I mentioned the city of Detroit was a good partner of Mapillary, uploaded all of the data from their mapping vans, and then helped us with annotating and creating the data set. So it basically looks like this. You got the 3D point cloud. You have these are their high resolution 360 images. You've got consumer grade, like all of the community images in the city. You got ground control points that were measured in the Mapillary annotation tools. You have annotations also annotated with the Mapillary tools, and then some aerial data that they acquired and donated to the data set too. And so all of these different modalities are registered into one big data set, which you can download and use. Next one is pretty interesting. A few years ago, there was a big drive on single image depth estimation to improve various different things. And it was really, really hard to get large scale data sets for this, and annotation costs were prohibiting. So we actually went out on Mapillary and created a data set automatically with 750,000 images. So we ran basically dense depth on the sequences, within sequences and between sequences, and we created these images with partial depth maps. But then, as you can see at the bottom here, the geographical coverage of these images is very different from your typical data set that you would find. And actually, this turned out to have a huge impact on some of the work that did later. But we're using this data a lot. Okay, and the last one, because we have in all of these places, we have collections from users across a wide range of devices, but also across time. So from the start to the end now, it's like over 10 years of collections. So in some places, you get some really interesting data that you could use for place recognition over large timescales, or large variability like seasons. So we created this data set. And as you can see, it's incredibly challenging. The marker on the map shows where the sequence is from, but basically we took sequences and then aligned them. And then it's over winter, summer, or like different lighting conditions, or like lots of developments in some areas. And it's a very challenging location recognition data set. All right, those are just 3 examples of all the data sets that you can find on that website. All right, some examples of what we built on this. So one of the data sets, which was called Mapillary Vistas, was we hired a company to annotate, I think it's like 10,000 images or so from Mapillary, chosen very carefully. And then we use that to train our production grade segmentation. So yeah, you can look at this. It's paper from CVPR 21, but basically we made some improvements to panoptic segmentation. You can see it here on the screenshot here, for example, around the poles on the right-hand side. Same fine level of detail, but also on 360 images. So this data and also all of the code and the trained models are available on GitHub. Oh, nerves. Okay, you probably heard about neural radiance fields. One of the things we wanted to do was apply this to mapillary images. So if you're familiar, typically you want like controlled capture for these things where you have like accurately computed pose, same type of lighting, same, all of the things that you don't typically have on a crowdsourced collection like Mapillary. So so there are some pros and cons of trying to apply this technology to Mapillary, but it's an active area of development for us, with the idea that we want to allow people to experience some places where we have lots of images, where there's potentially lots of interest. You can teleport in there and experience, for example, in VR if you want. And so this is like work on the path to that vision. And here's an example. If you saw my colleague Peter's talk yesterday, this is Times Square, and you can imagine all of the people that walked around Times Square and mapped with their phones across time. And then we're trying to create a nerf reconstruction based on that. But it's just like people moving around and like lots of chaos everywhere. And so you get something like this where you can see there's a lot of floaters and noise and junk in the reconstruction. It's because there are lots and lots of moving things that are sort of disturbing, ruining the results for it. But then you can leverage semantics and you can combine that. So here's an example of an image where we mask out like the sky and people and cars and things like that. And then you can improve on the results. And yeah, we put this live on the website. It's kind of an experimental feature, but you can go out and nominate areas that you want reconstructed, or you can go out and capture your own and nominate those, and they will start populating in the map. And then hopefully, as we improve on the technology, we're going to scale this up and make it available in more places and make it better quality. Okay, here are some examples from around the world. So these are just images that are available on the platform, captured with smartphones, using the Mapillary app. There's nothing specific, nothing fancy going on behind the scenes, but you can, at least in some areas, still create like a nice visual representation of those places. All right, so wrapping up here, if you want to get started, you can go to mapillary.com. You can click one of the many green big buttons on the site. That will take you to the map view, where you can click on the filter icons on the top left, and you can go in and search for whatever you're interested in. Or you can go look up the developer page, start using the APIs and download the data, download the images. Like I mentioned, the images are Creative Commons license. The terms of service gives you the right to use the derived data in any way you want, including commercial. If you want to integrate it into any tools, the viewer is also open source, or like I mentioned, the dataset page there. All right, great. Thank you.
How do you select the cameras? So there are many different cameras, and I think one of the most important thing is selecting camera. For example, field of view, frame rate, and lens distortion. So I'd like to know, how do you select cameras gathering teacher images in your works?
Okay, I'm going to repeat the question just in case people remote didn't hear. How do we select the cameras for this? So first of all, since it's a crowdsourced solution, we have no control over what people use, right? We can make recommendations, but so if you're mapping for a specific purpose, we can say this is the best equipment for you, right? For example, if you capture and you want to create a Nerf reconstruction, it's better to use the wide angle mode on your smartphone, for example. That's like instructions that we can give. But there are thousands of different smartphone models out there, and like we can't control what people use. But we did actually produce because we run self-calibration on the sequences, we did actually produce a pretty big data set. I think somewhere between 4,000 and 5,000 different cameras, where we have radial distortion and camera intrinsics for various smartphones and cameras that are out there. When we can see the make and model in EXIF that we added to that data set. Yeah, did that answer your question? Okay.
Yeah, thank you so much.
Thank you. We have one more here. Yeah.
Beautiful work. It's really exciting to see the tremendous breadth and quantity of images that are being uploaded, community building that's going on. From a technical point of view, since my interests have often involved around structure promotion, what do you find the most challenging aspects of calibration and pose estimation?
Okay, so the question was, what are the most challenging aspects around calibration, pose estimation? That's a good question. I don't know. I mean, it's all challenging to begin with, right? And it's sort of, when you do it this way, you accept from the beginning that you're in sort of best effort domains, right? So, like for example, when people use the data that's being generated downstream, they want guarantees on the accuracy of the positioning and things like that. And the best thing we can say is like, well, we have these reads from the sensors, and our reconstruction says this is reasonably accurate, but we can't give guarantees, right? And it's the same for calibration, right? Like we produce this data set, which we believe is a pretty good representation of starting point for camera intrinsics and radial parameters for most of the smartphone models out there. Is it accurate for every individual case? Probably not, right? But it's a best effort when it comes to a lot of those things. It wasn't a great answer to your question, but I hope it works. Yeah.
I want to upload something from Europe.
Yep.
Is there anything to consider? Because there are some draconic laws regarding data protection and intellectual property.
All right, and the question was if you want to upload from Europe. Draconic laws, I don't know. It's like that's a strong wording. GDPR is good for many things. But yeah, so I mean, I gave you the like crash course introduction, but of course we blur faces, we blur license plates, we don't store any unblurred images on the server side after it's been uploaded. In some cases, you can blur on the client side too. So yeah, and in certain countries, like in Germany, you have the right to take down images in certain areas. So there's like a geo-fencing solution for that. So if you live in Germany, you say, I don't want my street on Mapillary, then you fill out the form and then we'll cut that out with a cookie cutter. So yeah. Thank you. Good question.
Okay, now, yeah.
Good.
Very interesting work. Congratulations. My question is related to the panoptic segmentation.
Mhm.
You mentioned that you are adaptive methods that work for perspective image to panoramic image. What about the resolution? Are you able to keep the same resolution of the panoptic image, or you need to downscale?
That is a great question. So the question was about the resolution for the panoptic segmentation. You should, the details are in that paper by Lorenzo Forzi and et al. From 2021. But I don't think that there's any specific, it's not like we had to downsample when we went to 360.
You managed to patch the panoramic image.
Yeah,
And to run multiple inference.
it's not patched, it's run directly on the 360.
Oh,
Yeah.
okay.
Yeah.
Thank you.
And that was the surprising result, that it worked without having to create patches from the
Okay,
360.
and the image that you are using, they are even like 60 megapixel image for the panoramic image. No.
I don't remember what the actual resolution was for some of those results.
Okay.
But you can find it in the paper.
Okay.
But since we were looking for the fine details, we used high resolution images at least. Yeah.
Thank you.
Good question. Thank you. Pierre?
Yeah, you have an impressive tech stack like segmentation, structured promotion, etc. I was thinking from your perspective, what do you think is a solved problem, and what do you think the community can still help, like here at CVPR, which can be tackled to help such effort?
Okay, good question. So the question was, based on the tech stack, what are the areas that are solved and what are areas where we could get help? I would say the panoptic segmentation, for example, is an area where we can reasonably move on. Like it's good enough. The thing that we can get help with there is to add new classes, right? So if there are some things that are important for your use case, or some things that are not annotated in these images that you want, you could add that class. So you can maybe like try to expand the classes a little bit. Otherwise, I would say that the segmentation is a mostly solved problem. Yeah. Yeah, areas where research can help. Like I mentioned, like some of the recent work we're doing on radiance fields and trying to generate like a nice immersive view of a place, I think is going to become more and more important for a range of applications. Not just VR, and there's like, yeah, we need help, or we need like the state of the art to move further. Yeah, great question. Thank you. Yeah, one more.
If you have time for one more.
Yeah, I think we have.
I should probably, ask Peter more about this in detail, but have you been looking at Gaussian splatting?
Yes.
How do you compare those two models, which are more recent, to your texture map meshes that you can produce with your dense matching?
Okay, that's a great question. Okay, so the question was, have we looked at Gaussian splatting, and how does NeRF and Gaussian splatting compare to textured meshes? And yes, we have. And we have some, it's not on the website yet, but there are some papers on Gaussian splatting from Peter and the team, as you mentioned. And some of that will make it out into the wild, hopefully soon. In terms of difference, so I would say, yeah, Gaussian splatting seems to be very promising for these types of applications. One of the main differences, though, is if you want an immersive solution where you can move around, right? Then, and if you want physics, and if you want sort of like some of the interactions that, let's say you want to do a VR application here, and you don't want to just be there and look around. You want to be able to do the usual stuff you do in VR. Then you need some kind of mesh behind it, right? Maybe the right solution is a combination. So you get the nice photorealistic from a Nerf or a Gaussian splat, but there's some kind of world mesh aligned with it so that you could have physics stuff bouncing and you would know what the walkable areas of the floor are if you have this room, for example. So yeah, for certain applications, you absolutely need the mesh option. If you want pretty views, then yeah, we know what works best. Yeah. Thank you.
We have one question
Oh, yeah.
online.
Mhm.
How accurate is the latitude, longitude of point in the mapillary app?
All right, great. So the question was, how accurate is latitude and longitude for data on mapillary? It depends. In some places so we try to use the device estimate on GPS accuracy to weight when we do bundle adjustment. And so hopefully in areas where you have high quality captures combined with typically smartphone has lower grade GPS, we can snap to the higher accuracy ones, but it's on a best effort scenario. So there are no guarantees. Results have shown it's typically you can get to around a meter accuracy in most cases, unless you're in like urban canyon scenarios, you can get roughly a meter accuracy on the positioned objects, but it could vary. It could be 10 or it could be half a meter. It varies. Yeah, good question.
I think good. Thank you.
All right.
Thank you so much.
Thank you so much. Thanks for coming.
Thank you, Jan. Now we will move on to the next keynote speaker, Professor Ron Francier. He is a distinguished full professor in the Electrical and Computer Engineering Department at University of Laval, where he also serves as the Associate Scientific Director of the Institute of Intelligence and Data. Drawing on a wealth of experience, he previously held a pivotal postdoctoral role at Disney Research, Pittsburgh. He earned his PhD in robotics from Carnegie Mellon University in 2011, laying the foundation for an impactful academic journey. His research passions converge at the intersection of computer vision, computer graphics, and machine learning, driving him to explore the unification of physics-based model and the data-driven machine learning techniques. Through this pursuit, he aims to comprehend, model, interpret, and recreate the intricate aspect of our visual world. He boasts an impressive publication record of 70 referred papers cited nearly 5,000 times, highlighting the depth and influence of his contribution to academy. Moreover, he actively translates research innovation into the realm of commercial products, showcasing his commitment to bringing academic ingenuity with the real-world application. With 9 patents and a notable involvement as a scientific advisor for various high-tech startups, he is primed to bring invaluable insight to our event. I would like to welcome him for his next talk. You would have to connect to this one link. I will send you an email. It would have come to the
About that, just a sec. On screen.
you can see.
All right, all set. Okay, great. Thank you so much, everybody. Thanks for the invitation. And today we're going to be talking about adapting wide-angle lenses with distortion-aware transformers. Yeah. Right. Let's begin. So let's start with this 360-degree panorama, right? So we all know and love this here in this workshop, especially, which is, of course, in an equirectangular format, as we all know and love. But actually, let's go back to the beginning, shall we, right? And let's consider how this panorama was captured in the first place. Well, it's quite likely that it was captured using a 360-degree camera, such as, this one. This is the Ricoh Theta Z1 camera, but there are many, many other models. And in fact, in my lab, we've been using these kind of cameras for a long time now, and for many applications, such as, for example, we've used a similar capture setup to capture a lot of different panoramas in 360 degrees in high dynamic range over a wide range of different environments, where we have our beautiful mosaic transitioning to a beautiful photo of our campus. And this is what happens when graduate students have too much time on their hands. But we've captured roughly 2,400 HDR 360-degree panoramas. It's freely available on this website, so if you're interested, go ahead and have a look. And internally, we've used it for many things, including lighting estimation. For example, we train neural networks to predict the position and intensity of light sources present in a scene from a single restricted field of view image. In this case, we can use it for rendering a virtual object that as it moves around in the scene, the lighting on the surface of the object and in the shadows generated on the floor adapt as a function of the relative position of the object with respect to the lights. And I just want to attract your attention here that the light sources are actually not visible in the image, right? They're situated outside the field of view, yet the networks, they're able to interpret this and sort of, predict that, yes, a light source should be, to the left of the image at a certain distance. And I've actually talked about some of this work in this very workshop a couple of years ago. More recently, we've looked at NERF actually, but NERF in the context of by using 360-degree cameras. So I have my student Momo here. His face is blurred out, I guess, for privacy reasons in the paper. Anyway, and we were attaching two 360-degree cameras, so like butt to butt, I guess. One of them is capturing a regular video. Another one is capturing a video at a very fast exposure. And we train a NERF on the set of these two sets of images. And we can actually reconstruct a NERF, essentially, so a radiance field, but in full HDR, where we capture not only the appearance of the scene, but also the intensity of the light sources. And we can insert virtual objects like this at different spots in the scene, and actually we can kind of turn around, and you can see the armadillos on the tables. They're kind of brightly lit, and there's some tiny ones under the tables, and those are dark, of course, because they're under the table. Just a brief sort of overview of the kind of stuff we do in the lab. But today I actually want to kind of go back to these cameras and consider the actual lenses that were used on the cameras to capture the 360-degree field of view. And of course, these cameras, they have wide-angle lenses, right? And that's very useful because with like a single shot, you can see with every one of these two individual cameras, you can see them sort of side by side on the image on your left. They have very high field of view, right? Maybe 180 degrees or sometimes even more. So that makes sense, right? Because, if you were to use regular cameras with regular lenses, then, you'd need a lot of different photos, 1, 2, 3, 4, etc., to get the entire 360-degree field of view. And that's useful in many applications because, if you see more field of view with one camera, then you can save on bandwidth, you can save on money, you can save on memory, right? So it has a lot of advantages. So they've been used in many things, like I don't need to convince you of that here, of course, security, healthcare, autonomous driving, etc. But unfortunately, they come at a cost, right? These wide-angle lenses come at the cost of creating distortions. So I can have a single lens that creates, an image that looks like this. And of course, it's one of the images coming out of a lens, say, and if I look at the building on the left, you can see that it's sort of tilted inwards, right? And then on the right, well, it's tilted the other way. But that's not the end of it, right? So the distortion actually depends on the lens that we're using. So a different lens might have a different distortion, and perhaps another one, and perhaps another one, right? So if I come back to the application of let's say, autonomous driving, focus on the task that we're asking our network to do for a second. Well, the network actually needs to reason about the objects that are present in the scene and perhaps needs to detect the object over here on the left, maybe this person. It's because that person is standing on the left of the field of view, it's going to be tilted in such a way, right? And then this other person on the other side of the field of view will be tilted the other way. So when we train a neural network on this task, well, it has to adapt to that, right? And let's say it has a large enough data set of images coming out of that lens. Then, as it learns, it can build essentially a spatially varying prior that says, well, if I'm looking at stuff on the left, things should be kind of tilted in such a way. And if I'm looking at stuff on the right-hand side of the image, it should be tilted in another way. And if I'm looking at stuff in the middle, things should be a little bit bigger. Right? And as I move away from the center of the image, things will get smaller as they get kind of squished on the side of the field. Right? So can learn these things provided we have enough training data. But the question that we're asking, I'm going to ask in this talk is, what if the lens changes, right? What if I suddenly decide that, my first lens, I don't know, I don't feel like I'm liking it anymore. I kind of want to change it. I'm going to use this lens instead, right? That has a different distortion profile. Well, in this case, the priors that I have learned on my previous data set with my previous lens maybe no longer applies, right? Because now my lens and the other lens is creating a new distortion profile that I've never seen. And you know, the different priors that I've learned, and here I'm just, you know, this is just like a mock-up, I guess, but to give you an idea, right? The previous priors that I learned beforehand, they no longer applied because my lens has changed. So what's one to do, right? Well, if I decide to change the lens for my application, then perhaps the thing that I need to do is go ahead and collect some more data, right? I'm going to go back, maybe install a camera in the car, drive around, have some, hopefully hire some labelers, you know, and get additional labels, and then fine tune maybe my pre-trained model on that data set, right? And then if I want to change it for another application, then I need to kind of redo this all over again. So our goal in this presentation is going to talk about that specific problem of adapting. Oops. Realize that this thing is kind of, here we go. It's kind of hiding the title. So adapting to the distortion, right? Can we design a network? Can we design a method that will be able to take an image as input and essentially, you know, accept that specific image? And then if I give it another, if I give it another lens, an image of another lens, then I should be able to adapt the network automatically to that lens. And here we're going to make the assumption that we know something about the lens, right? So we're going to operate in a calibrated case, and I'll discuss at the end, you know, what we can do if we don't have information about the lens. Well, in the literature, if we check out what we can do, the existing solutions to this problem of adapting to a lens that we've never seen at test time, well, one easy or sort of straightforward solution is to simply undistort the lens, right? So back to, let's say, a projection that we all know and love, for example, the perspective projection. So if I have this wide angle image that has a 150-degree field of view, I can unwarp it back to a perspective projection, let's say at 90-degree field of view, and I'll get an image that looks very reasonable, and I can run any network on that. That's fine. However, this is a reduced field of view, right? 90 degrees. What happens if I want to keep the field of view original? Well, I'll have a lot of stretching, right? So perspective projection at 150-degree field of view looks like this. It looks fine in the middle, but as I move away from the center, things get stretched. And this is, quote unquote, only 150-degree field of view, right? We want to be able to deal with much higher field of view, including all the way to, let's say, 180, at which case things get stretched really, really bad. And actually, I have a 16-year-old daughter. And the other day she was telling me, oh, look, you know, now we take, I don't know if you guys know about this, but there's this new thing that, you know, the young generation does, and it's called the 0.5 selfie. You guys know about this? Yeah, you do. You have a 16-year-old? Right. Anyway, so the 0.5 selfie is this thing where kids, you know, they take selfies all the time, of course, but they put their cameras in 0.5x mode, you know, so the zoom out essentially, which turns on the wide angle camera apart, you know, that are present in new phones. And then they just rectify it. Basically, the app rectifies it for them, and you get these beautiful photos like this. So yeah, so they post this on Instagram and they have fun doing that. So anyway, so this is you know, perspective projection with a wide angle image in action. You get these beautiful photos. Apologies, that's stuff of nightmares. Apologies for that. Oh, okay, back to business. So on distortion, you can actually, because perspective projection is not going to work with wide field of views, you can use other things like there's cylindrical projection, but there's also the piecewise perspective projection that looks like this. It's like a cube map, or partial cube map rather. And you can get that so you don't lose the field of view, but then you create these weird discontinuities. Over here, for example, the person is split in half, so it creates these weird artifacts that we're not too happy with. Solution number two could use deformable convolutions. So how some people have proposed, rather than using a conventional CNN, that applies, let's say, the same filter, you know, everywhere in the image, you can actually learn to deform that filter. And that deformation, it can be spatially varying, right? So you can kind of adapt to the distortions that way. But that's unfortunately usually much more computationally expensive, you know, because you have to have this extra step of distorting the kernel. And then, you know, since you distort it, it's not the same everywhere. So you cannot do this efficiently. So it becomes very, very slow. Okay, so in this talk, I'll actually present an idea we've introduced last year at ICCV and that we're still pushing in my lab nowadays. And essentially, the idea is to be able to adapt the network structure to the radial nature of distortions without having to undistort and without having to rely on deformable convolutions. I just want to do a quick shout out to my student, Akshaya. So this is his work, and these are, most of those slides are actually his as well. So I was, the lucky advisor just kind of stealing slides. But actually, he actually made a presentation, like a student presentation recently, and won an award for this presentation. So I figured, why not, right? So, but this is mostly his work, and I'll talk later about 2 other students that were involved. Okay, so let's dig into some of the details. All right, so our approach is going to rely on vision transformers, which take an image, split it into a set of patches, and then computes attention of those. So I know you guys know essentially all about this already, but let me just do a very quick recap of how the transformer works, because we're going to be taking some of these ideas and see how we can adapt them to the case of a lens distorting the image. Okay, so Transformer 101 is basically you take an image, you break it up into little patches. Then you take all of these patches, you project them to some sort of learned space. You get what we call token embeddings, and then you give them to the transformer encoder. What the encoder does is that it computes the attention between one of the tokens and essentially all the others, and determines the attention is like how important is that token to all the others. Now, of course, as is, the transformer doesn't know where these patches come from. So in order to provide that information and say, hey, look, this patch actually came from, let's say, the top left of the image, then we're going to add a positional encoding, which is some sort of code that says, hey, here's where this patch came from. So then the network can know, oh, yeah, I'm looking at the top left corner of the image. More recently, there was the approach called SWIN, for shifted window attention transformer, which instead of splitting the image into a grid of, let's say, 4x4 patches, it does so in this sort of hierarchical manner. And instead of computing the attention from one patch to all the others, it does so within the small regions, right? So it will compute the attention between this little patch and all the others within their own kind of small window, and then aggregate spatially and do this in a hierarchical manner. And in this work, what we do is actually we extend on the SWIN, and we propose what we call the distortion-aware radial SWIN transformer, or with its little name, DARSWIN. Of course, Darwin has the goggles, yeah. Wide-angle lenses as image. Okay, great. You all got it. So this brings me to so our goal, with the distortion-aware radial SWIN transformer, is to design a network that will be adapting its structure to different lenses at test time without having to train on a given lens. Okay, so let's dive in the overview of the method in more detail. So you'll see that we're going to repeat or sort of take every single step of the way of what happens inside of the transformer and see how we can adapt it to the case of a wide-angle lens. So first of all, let's take a look at how do we break up the image? How do we partition the image into the patches that I was mentioning? So the regular SWIN does it in a Cartesian grid, and essentially all previous transformers do it in a Cartesian way. But of course, wide-angle lenses, they have a distortion that follows in a radial manner, right? So instead of Cartesian, we're going to split the image in a radial manner like this, which sort of looks like a, like a pizza or like a pie. But we're going to do this in a way that conforms to the lens. And what I mean by this is that we're going to use the lens curve, which characterizes how the lens distorts the input rays. So, for example, if I have this image, this lens here on the left, what a lens radial, like a wide-angle lens, does is that it maps a ray coming in at theta I, at angle theta I, and will map it on the image plane at a certain radius Ri. Right? And there's a function over here on the right that determines how the lens does that. And the function, will have a curve that looks something like this. So our key idea in this work is that instead of splitting things, in a regular manner along the azimuth and radius on the image plane, we're going to we're split things equally along the azimuth, right, at equal distances. But instead of doing that at equal distances in radius, we're going to actually do it at equal distances along the angle and rely on the distortion curve to tell us where in radius we should split it. All right. So according to that curve, I should actually be doing my split this way. And if I'm given another lens, right, that curve will change. Another lens, that curve will change. And so will the image, according to that curve, right? So in this case, all I got to do is essentially I keep the split constant along the angle, look up the new value along my curve, and shift the way I split the patches according to that lens, right? So this is a distortion-aware way of splitting up the image into the tokens. Okay, so this is step one, which was our image partition. Step two was to compute the token embedding layer, right? Which was said, I'll start with my tokens, and then I'll turn them into this latent code. I start from my image patches, sorry, and I turn them into this latent code. So how do we do this? Well, in this case, now that we have these pie slices, right? They unfortunately are not of equal size, right? So they don't have the same number of pixels in both of these slices. So I can no longer just apply, let's say, the same MLP everywhere. So I have to think about it differently. So what we're going to do here is simply rely on sampling. So we're going to define a sampling pattern on a patch and then adapt that sampling pattern to the different patches according to their coordinates and according to the lens distortion as well, and essentially repeat that sampling pattern everywhere to create essentially a polar representation or sort of a polar warping of the image according to bilinear sampling. And finally, we get that polar image, and then we turn it into this latent code using a simple CNN. Okay, this was for the token embedding layer. Now let's take a look at the transformer and the positional encoding. So quickly, the traditional positional encoding in a SWIN or a VIT is done in this way. So you take a token and you essentially look at, you encode how many hops do you need to do to move to another token, right? So it's called the relative positional encoding. So all you have to do is like, if I have these two patches, let's say the highlighted one in the right, and the one on the far right, I've moved by +2 on this side and 0 on the other dimension. So that's what you tell the network, and the network will learn, it will learn that according to the differences between the patches, the token. And that same goes for, the number of hops in the, let's say, the vertical dimension. So in our case, we're gonna, we use our radial patch positioning. So we could do the same using radial, right? Just simply by counting the number of hops, -1, -2, -7. But unfortunately, because of the circular nature of a radial pattern, the this patch and the one on the -7, they're actually situated right next to each other in image, right? So that cannot work. So instead, we're going to simply use an angular positional encoding, right? That encodes, instead of encoding the number of hops, we just encode the delta angle between two tokens. So let's say pi/4, 3pi/4, and 7pi/4, which is equivalent to -pi/4, right? On the other side. So that's for the azimuth. And then for the radius, again, we'll use our curve for the radius to say, the hops that we have between two tokens over here depends on the delta theta inside. Okay, almost done. And finally, actually, that's pretty much the end. So we're going to merge patches in a hierarchical fashion and then redo this many times until we have our entire encoder that essentially repeats those same blocks. And you can see here, the lens curve on the left actually gets injected inside of the network at multiple places, so that the entire encoder in this case is distortion aware and can react to changes in the lens. Okay, so let's take a look at our goal again. So we had this image, I want to train a network on this image, and then I want to test it on another image. So how do we know whether that works? Okay, so right now we're only have an encoder, so nothing too complex. So we cannot predict pixels again yet. So we're gonna test on classification at first to see whether the idea works. And for this, there is no data set of differently distorted images at wide angle for classification. So we essentially built our own with the synthetic distorted image net, where we take the image and we apply simulated distortion. And here we use the spherical distortion model, which is quite useful because you can only vary one parameter and you change the distortion. So it's just one axis to explore, which is nice. And it's also invertible. So you get you get the equation for the invertible mapping, so you can get perfect on distortion to compare. Okay, and this is how I'll report the results. This is a plot of the accuracy on the y-axis as a function of distortion on the x-axis, which ranges from 0 to 1, 0 being no distortion, 1 to be very high distortion. And the pink region over here represents the set of images that were used for training. Okay, so I'll train on images only in that pink region. And then you'll see that I'll test across the whole range. My goal being that I want to have a curve that's as flat as possible, right? Of course, things are going to go down. Okay, I just want to set the expectations, right? That's one thing that I admit. Set the expectations, right? Things are going to go down. We just don't want to go down as fast as the others, right? Okay. All on board? Yes. Okay, good. Just to give you, these are the kind of images, and things get pretty crazy. So if we train a SWIN and its more recent version of a deformable SWIN, so essentially it's the same kind of idea as the deformable convolutions I mentioned earlier, but with attention. So this is the deformable SWIN, and this is the original SWIN. You can see that while they do good on the training region, their performance falls pretty fast. Right? And when we try our approach that adapts to the distortion, we get this. So yes, it's still falling, but hopefully it's not falling as fast. But I'm pretty sure you're all going to ask me, but wait, this is unfair, right? Because your approach, Darswin, this is you talking to me. So your approach, Darswin, knows the length, right? And SWIN and DAT do not. They don't know, they're uncalibrated, whereas yours is calibrated. So like, this is unfair. So that's a point. If you ask me that question, I'll say, I'll agree with you. And that is actually unfair. So how do we make it fair? How do we make it a fair comparison? Well, we can essentially undistort the images, right? So we can take the input image and undistort it according to the distortion, which we know. And I mentioned earlier that the distortion model we use is actually perfectly invertible. So there is no mistake. We don't use a network to try to estimate it. We don't use a non-invertible model, right? So it is invertible, it's perfect. So we can get it right. Actually, surprisingly, when we did that, this was the result. So we trained the SWIN transformer on undistorted imagery and then tested again on undistorted imagery. And we found that the performance dropped quite drastically as well. And we think that it's due, well, the resolution is relatively low in these images, but we think that it's due to the fact that, when you undistort, you create these stretching artifacts that become more and more prevalent when you have very high field of, lots of distortion, and this penalizes the network. Okay, now the question is, can we go beyond image classification, right? Can I go and do perhaps pixel level tasks? Essentially for this, we're going to need to extend our encoder, right? This is an encoder that takes the image and compresses it to some low resolution latent information. We would like to decompress it back to another image to do pixels to pixels. And so we can actually very simply repeat this process of essentially copy paste all the methods, all the different blocks. I apologize. And then so like the transformer positional encoding stays the same. Instead of merging the patches, we can expand the patches. So we can replace patch merging by patch expanding. And at the very end, instead of partitioning the image into tokens and then sampling the image to generate the tokens, then we can actually, we need to go from samples back to pixels. And here we can do it with a simple nearest neighbor approach. So we're going to test this on depth estimation using images from the Matterport 3D dataset. And for this, we can simply generate training data by taking a panel that also has the associated depth information. And then we can, extract a wide angle image, rotate the panel, do this again. And we can do this many times to create our training set and test set, of course. And we end up with this synthetic wide angle image dataset using Matterport 3D. Again, our worry or our interest here is not necessarily in obtaining the absolute best performance at a task, because there are plenty of networks that try to get the best possible depth estimation at a given task. What we are interested in is the adaptability of the approaches to the case where the lens is changing, right? So as with classification, what we'll do here is that we're going to train the network on, let's say, one of those groups. Let's say we'll train it on the very high distortion in this case, and then I will test it on an image at medium, low, and very low distortion as well to see if we're able to kind of stay flat. And the results for the depth estimation are shown here in this slide. So again, we're going to train now, instead of training on the low, I'll show you results on the right, on the high. Sorry, so the pink region is the training region. And we'll test across a whole bunch of different distortions. And here we tried many different approaches because the existing methods, the SWIN, for example, is only an encoder. So you can choose what decoder you'd like to use. So in the SWIN paper, they use UpperNet. And then we also tried using a UNet-like SWIN decoder. And also we tried using the undistortion, right? So the blue and the orange curves, they use the undistort. So those would be like the calibrated different approaches. And then in our case, we have achieved that performance. So it's a lot flatter. It's not quite as high over here in the training regime, but it's able to stay flat until it reaches sort of the end where it starts to drop. Okay, so I guess that's what I had for you today. So in summary, I presented to you a method we named DARSWIN that takes as input a wide angle image as well as its distortion curve. And we tried it on a couple of different tasks. We're trying it on semantic segmentation and other tasks these days. And we're also experimenting with the case where the camera is not calibrated. And for this, we have just preliminary experiments where we show that you can, the simple approach for this is like you train another network for estimating the curve. That seems to work relatively well on the data sets we tried. But we're also very interested in seeing, can we make these networks sort of adapt to the lens without having to do this two-step process of, one network for calibration, another network for, let's say, the task you're interested in. Hopefully, maybe I can, be back next year or soon, to tell you all about it. All right, so before I conclude, let me just thank my students again. So this was mostly the work of Akshaya. Also, Ishraq, she worked on the depth estimation experiments, and Emil was an intern with us who helped quite a lot, achieving these results. And with that, I would like to thank you for your attention. Be happy to take questions.
Really amazing talk.
Thank you.
Congratulations for your work. I have two questions.
Sure.
One question is related to the attention maps.
Yeah.
Did you have a look then? Did you notice some interesting patterns for the DARSWIN?
So the question is about the attention maps, whether we looked at them, if they have an impact. Actually, we don't remember. I don't believe that we did. That's a very good point. I think we should definitely take a look, see what lights up, basically. Yeah.
And the second question is related, you at the first slide you showcase the recall data.
Yes.
And there are two wide angle lenses. Did you think about, use the technology to put together the things and to have something that is able to, to recover, depth estimation without converting to a rectangular projection?
Right. So I guess the question is about, for people on Zoom, whether we thought of using, let's say, the two cameras in the Ricoh in order to do the depth estimation, as opposed to having to go through a clear rectangular and do the rest. We have not. We were mostly concerned about sort of one lens at a time, how we could do it. With a system of multiple lenses, that would be interesting to see whether we can. Well, the thing with these cameras is that the lenses have very little overlap, right? Because they only have overlap on the side, basically, and they use. I'm pretty sure that the software in there uses that overlap to stitch, right, to make sure there's no visible discontinuities.
I expect that probably your technology would be able to avoid any kind of stitching.
It might be able to help. Yeah, exactly. That's kind of what we wanted to see, whether we can, without doing the undistortion, without doing the stitching, can we do the reasoning directly on the lenses? Exactly. And especially be
but
able
you
to
planned
adapt.
already.
Was that?
I think you planned already, right?
Yeah, well, hopefully.
Thank you very much.
Yeah, you're welcome. Thanks for your question. Yes, in the back first.
Yeah, I just keep continuing.
Yes.
Questions. I, like in the cars, we now have fisheye cameras and people.
Mm-hmm.
And then they share sometimes.
Correct.
Can your method apply to this kind of situation?
Yeah. No, that's a really good point. And we've been looking at that actually, trying to study whether we could, oh, sorry, the question was, in many applications, let's say cars, right, they have wide angle lenses as well as regular sort of perspective projection lenses like pinholes. And the question being, can we, exploit those too? And the main challenge we're facing in this case is that of a different field of view. So where, for example, we were looking at how can we use this to, let's say, train on a perspective image and test on a wide angle. There's a lot of papers that look into that, like with domain adaptation techniques and things. So we were trying to see what we could do with this. The challenge here is that as we're encoding, where we're training the Darwin transformer, we assume that we know the entire field of view, right? We see the entire field of view. So if we only have a restricted field of view, then the wide parts you don't see, right? So we're thinking of, oh, can we like do some data augmentation to, sort of simulate that we're looking around the field of view? So that would be a possibility. But certainly, I think if we had this pair of data, as you mentioned, we could definitely use it. And and yes, indeed, there are some patches, for example, here, right? So we sample the same number of samples per patch. So some patches take up a huge part of the image, and the other ones, like on the periphery, are very thin. So this is actually an issue, especially when we want to decode back to the image. Meaning, let's say we want to do depth estimation, we want to have an answer at each pixel. But we reason on the samples, right? So the sampling pattern is actually very important. And in fact, this is a very good question, and we've been sort of banging our heads on the wall for a bit on that one. And the answer that we're coming up with right now actually is about how do you sample on the angle, right? Because here I told you earlier that we sample equally on the angle axis, but actually. I don't know if you know a bit about fisheye, right? You can sample equally along functions of the angle, not necessarily theta itself. But you can say I'll sample equally along tan theta. That would be like for a fisheye, right? Or I sample equally for theta, or I can sample equally for f of theta. Now the question is like, what should f of theta be, right? Such that you have samples that are as equally distributed as you possibly can on the surface of the image, but you want to keep in mind that this needs to work for highly distorted images and also images where you have very low distortion, because we want to be able to adapt. So we're hoping to submit a paper on this soon, but the solution we've come up with is to essentially, we have a family of functions that are invertible, defined over the 0-1 interval. And we essentially optimize for its parameters to say, give me the function that such that if you sample it equally, will give you samples along the image that are as, let's say that are as equally distributed as you can, right? So we can optimize for this, and we do find actually that there is a function that exists that's sort of a good compromise between, let's say, tan theta on one side and theta on the other side that are kind of the two extremes. And it gives you something that's like better distributed. But your question still, like your point still remains, meaning some patches are going to be bigger than others. So the resolution is not exactly the same. Yeah, can't get away from that, unfortunately. Yes.
In data set generation, you said that distortion constitutes only one parameter.
Mhm.
However, distortion is various patterns with non-orthographic, equidistant, ipsoid angles. Can does we adapt all feature ranges?
Yes, good point. So the question is like, I've used, we have this distortion model that uses a single parameter, but if I summarize what what you're saying, there are many other different types of models, right? In our case, we rely on the curve, basically, right? So if you provide the curve, whatever parametric form it may have, we can just sample from it directly. So, and in the paper, we've also tried, let's say with the Woodscapes, data set, has calibration data. They use a polynomial distortion curve, right? So we can sample from that polynomial directly and then use it to partition the image and embed that in the transformer as well. The only downside of it is that it's not invertible. So it's not directly invertible. So, you're doing the undistortion might have errors, although I think it's a sort of a good polynomial so you can actually do it without too many problems. But yeah, as long as we have the curve, we're able to feed that to the network without problems.
Thank you so much.
Thank you. Yes.
So when you are using fisheye images, you have vigneting effects or other
Yes.
effects that appears.
Sure.
Do you think that this can be used too, or is it just learned by the network for immediately?
Yeah, that's a really good point. The question is about vignetting. Vignetting as that can arise as we have wide angle images. In this case, we don't actually simulate it. So we're, the data, the results that I've reported were on simulated data. So we don't actually use that. In practice, this will arise for sure. This is certainly something we could leverage as well. If we had a model for it, most lenses, as you calibrate them, will have a model for vignetting. Because as you generate, let's say for the theta, right, you want to generate a panel. Certainly, you don't want the panel to sort of become darker and then brighter again. So we could certainly leverage that as well. Yeah, good point.
Any more questions?
More questions? We're all good?
Thank you.
All right. Thank you very much, everybody.
Thank you, Professor. We are going to take a short 5 minutes break, and then we will be back with the oral presentation, where each paper, we have 4 oral presentations, and each paper is going to get 15 minutes to talk about their work, and then 5 minutes for question and answer.
That was really cool.
Thanks.
I wasn't aware of your work.
Okay.
We have actually done something that's quite close.
Oh, really?
Yes.
Cute to you.
Yes, exactly.
Well, that's what, you know.
Yeah, we have them also.
Like here?
Yeah, the main.
Oh.
Yeah.
Cool.
So because
When is it?
I think it's Wednesday. I mean, what? I can send you.
Yeah, that'd be great,
Yes. So what we did, so we also looked at swim.
Okay.
We also looked at sort of this fisheye problem.
Okay.
And I mean, it was very nice how you raised it with data. So I should tell, so I work in Sweden. And we are in the market.
Okay.
And so we looked at, spherical models and then we started looking at fisheye cameras, but they are not computer vision people.
Okay.
So we hadn't thought about sort of different lenses and things.
I see,
We only
yeah.
looked at fisheye.
Here, fisheye.
And then we thought, okay, so can you just project everything back into the real world? There's these method functions you get. So. And then it's naturally an image on the screen.
Right.
Right.
Yep.
So that's how we thought about it. And then then the idea is, okay, how do you make spin so that you would nice the sphere? And how do you sample the sphere nicely? That's why I was asking, because there are spherical models, but they use equi-rectangular coordinates, and it's really nice and really crappy around it. And so then we transfer some different grid field picks, and it comes from sort of satellites that do sort of observation.
Yeah, a lot of people have looked at that, right?
Exactly. And then we use that on Field Swim. And I mean, there are some nice aspects because it's also the skyline. It's so that it lines well with the caching and the way. So I think it's more. Yeah, I mean, I could look it up, but
Absolutely. That sounds, so again. Basically, this, well, not the same ideas, like exactly the same problem.
Yes, exactly.
I don't, vision background, so we're going through the space, we're trying to see like.
Yeah, so you have this cameras and you know actually what you're doing. It's just playing around with it.
But you think, I mean, we've been considering, we're learning about these things also. This very sort of technique.
Yeah.
They're very much like.
Okay.
You're exploring.
Yes.
Whether you design these network activates that like
Yeah.
regular grid.
Yes.
So I mean, if you think about, so what I've shown is essentially actually very similar. Except that instead of doing it in Cartesian, we do it in polar. The polar representation, has the wraparound and all these things, but and we also augment with the length distribution information. But at the end of the day, if you look at it carefully, it's like spinning polar. Hey, it's okay. And then, but the problem comes from converting to polar. This is where the sampling is from.
Yeah.
Right. And this is where all the issues are. It's basically.
Yes.
I think in your case, if you do it as vertical, you have perhaps less issues with the sampling.
Yeah, so I mean, there is an issue with as well, right? And this is that, hey, you can project it out sort of into the theta pi domain as well. But then, of course, you have some grid on your sphere. So that means you need to be some.
We would like to start our oral presentation.
Yes.
Hopefully everyone is gonna get back soon. The first presentation selected is Sensor Equivariance, a framework for semantic segmentation with diverse camera models.
So thank you for the introduction, and let me introduce myself. My name is Hannes Reichert. I'm a PhD student at the University of Applied Sciences in Hamburg. You probably never heard of us, but I will use this this talk to introduce our working group. Actually, in the next slide. Yeah, better? Good. So we are a really small university in Germany, so like 3,000 students, and two handful of PhD students, so nothing big. But we do quite some research. Our lab mainly in the automotive domain, with some key partners like BMW, Bosch, Valeo, Continental. And we do two things. Mainly, we operate a research intersection located in Aschaffenburg. So that's one public intersection, and we place a lot of sensors there, cameras, lidars, radars. And we use this to monitor the traffic, to extract trajectories of vehicles and pedestrians, and yeah, use this as a data source for our own research, but also for industrial partners like Bosch or Valeo to evaluate their algorithms at our intersection. And the second thing we do is a research vehicle. So we got a full stack research vehicle equipped with everything you need to drive autonomous. And we got a full sensor suite actually hidden in the chassis, like fisheye cameras, lidar sensors, radar sensors, and so on, and also drive-by-wire. And we just added a rooftop-mounted sensor suite consisting of a Auster sensor, a lidar that's quite a high-resolution lidar, and a Ladybug 360-degree camera. So yeah, high-resolution panoramic camera. And we use this to collect data in Aschaffenburg, Germany. So to the agenda for today, I don't have many slides, but I will talk a bit about the problem statement sensor equivariance. I will give you an introduction to our solution to the problem. We had another solution in the last talk. I give you some overview of our data set and data augmentation pipeline, show you my results, and show you the future work. So to the problem statement, sensor equivariance is mainly a generalizing problem or generalization problem. So we want to build computer vision algorithms that work with as many cameras as possible and with as diverse intrinsics as possible. And so I borrowed this fiction for the equivariance definition to display this in, as would say, in a graph. So mainly we have two different cameras on the top, one with a vehicle, with a small vehicle, one with a bigger vehicle. And we got like our transformations age, where we can go from, let's say, a wide angle camera to a narrow field of view camera and vice versa. And we got our feature extractor theta that extracts features from the image. That could be a neural network or a transformer, anything. And we get features down there that we, by definition, want to be able to transform back with the same operation to the other image. Why is this important? Yeah, mainly because if we talk about the domain we are coming from, automotive, we have usually the problem that people build a full stack research vehicle or development vehicle, and they put a lot of effort in there to mount a camera system, to mount a lidar system, to get the data annotated and recorded, and to train networks. And then we have like an issue, because at this point we can take the networks and put them to production or to deployment if we decide to change, for example, the cameras. That's usually is something that happens at this stage of development, because usually you're forced to use cheaper cameras, you have to cut prices, sometimes requirements change and so on. And you also have to integrate the cameras into the vehicle body so people don't see it. And so we need a solution for that. And our solution is an equivariance network. For this, we have two parts. One is a sensor encoding. It's quite similar to what we heard before. Mainly, we use the principal axis of the camera and encode the angle of a pixel where the light propagates through. And we can do this for any calibrated cameras. So pinhole cameras, fisheye cameras, and so on, as long as we know the calibration and yeah, we have the data for that. So this angle we call deflection angle alpha defines actually a unique point on the image plane for every pixel view. So only the angle doesn't do this, but the angle in its neighborhood does it. So to give you some examples how this is looking like, we generated some data in Scala, and I have here 5 cameras, all with different intrinsics, and these circles are visualization of this deflection angle. From the inside to the outside, it's always 10 degrees. So the camera from your side or your point of view left has like 30 degrees field of view, and here on my side we have a fisheye camera. So another part we use is something I call sensor conv. It's a quite simple extension to a convolution operation by just adding this deflection metric at every convolution stage we use. I would say it's more old school compared to the transformer architecture, but yeah, it works as well. The next thing is data. So you learned before that data, especially for fisheye cameras, are hard to get. Especially if we talk about annotated data and we have to fulfill some requirements for that. So we came up with the idea to generate our own data in the color simulator. For that, we designed a virtual sensor suite in the color simulator and stitched the panoramic image. And then we use this panoramic image and the unified camera projection model, UCM, to augment image with various field of views, resolutions, distortions, and so on. And actually, this data generation process is open source, so I added the code to my paper. We decided to put a data generation process open source and not the data set, because we are talking about high resolution panoramas, and uploading it anywhere would use a lot of storage. So if any one of you want to use it, you have to generate it by yourself. So next up, the results. For our experiments, we used some baselines. Unfortunately, I didn't use some state-of-the-art baselines like the camera encoding in the Omnidirectional paper, but it's something I will do for my PhD thesis in the future work. So we used as baselines a normal ResNet, one time pre-trained on color on Coco data, and one that's not pre-trained. So we got the base with the star, that's the pre-trained one, and the without the star is not pre-trained. Then we use a ResNet pre-trained on Cityscapes dataset. And for the Cityscapes version, we don't augment the camera intrinsics. So we just keep intrinsics quite similar to the Cityscape ones. And the other ones are QuadConf and CamConf that are two other sensor encoding methods, and the SensorConf method from us. And as you can see, results vary. depending on the field of view and the distortion of the camera. And to give this in numbers, we did a statistical evaluation. So we generated, for evaluation purposes, 81 different cameras. 81 different cameras with large field of views, with narrow field of views, with high distortion, with low distortions, and with high resolution and low resolution. And we evaluated the methods on all these data sets we generated with this method. And we provide like a box plot on the left side of all these individual data sets. And we also do a statistical significance test. I assume some of you are not firm with this. So let me explain the graph on the right slightly. So basically, that's a statistical ranking done by AutoRank, and it basically ranks the performance of a machine learning approach among various data sets. And on the top left, you see like the bar for the critical distance. So this shows you if something is within this critical distance, you can't see any significant distance between the methods compared. And as you can see, we can show that we get a significant improvement over the baseline that's pre-trained on COCO data, and even more significant improvement over the other approaches, with the one trained only on a single field of view on the far right side being the worst. So next up is my future work. So we did this for semantic segmentation. So now we want to go a step further and do this for depth estimation. So you can see some preliminary results. It's also done with the Kerala data set we generated. And we use this to train sensor equivariant metric depth estimation method. It's working quite well, but we still have some issues to overcome. Mainly issues that are known for depth estimation problems, like long tails at small objects like pedestrian and be here. And that's something we are working. We have some ideas, but yeah, it's still not perfect. Okay, so all from my side. Thank you, and I'm here for questions.
If we have any questions on. Yeah, thank you. Thanks for the talk. Now we have the second paper presentation, estimating depth of monocular panoramic images with teacher-student model using equirectangular and spherical representation.
Good morning, everyone. Can you hear me? Yeah. Good morning, everyone. Can you hear me?
Yeah, you are audible.
Okay. So, could I share my screen?
I think we can start the presentation. I think our presenter is via Zoom call.
Oh, okay. So, good morning, esteemed experts and scholars. We are the research team from Southwest University in Chongqing, China. I am here to present our research titled Estimating Depth of Monocular Panoramic Image with Teacher-Student Model Fusing Equirectangular and Spherical Representations. I will focus on 4 aspects: motivation, method, result, and thinking. To begin with, let me introduce the background and motivation behind our study. So we know that the wider field of view means richer visual information. So estimating the depth from a single 360-degree panoramic image is an interesting topic. Since a 360-degree panoramic image is usually represented as an equirectangular projection, that is ERP. This problem is formulated as the estimation of depth from a single ERP image concretely. However, the problems of disconnectivity and distortion arise. How to coping with this challenge is tricky. Although, the page, yeah. Although a cube map representation can improve the distortion of an ERP image effectively, it has its own limitations. First, since a cube map representation is made up of 6 square perspective images, padding operations is necessary when carrying out convolution on the boundaries of each perspective image. Next, theoretically, a cube map representation is not an ideal one to cope with image distortion, because a perspective image has its own distortion. So what about tangent representation? It represents the panoramic image with any number of perspective images. Due to the large number of views, there is a significant amount of redundancy in many regions, and the fusion processing of these repetitive regions will bring new issues. Now let's see spherical image. It is known that an ideal representation for a 360-degree panoramic image is a spherical image, because the distortion of a seen object does not change with its position on the sphere. This isotropic property makes it superior to other representations. Therefore, in our work, we estimate the depth of a monocular panoramic image by fusing a spherical representation with an ERP image. A spherical convolution method is also developed. Moreover, the future map extracted by the spherical convolution is fused with those extracted from the ERP image to achieve better performance than the existing method. How to learn the features of depth images better? Inspired by knowledge distillation between an encoder-decoder structure with depth image input, also depth image output, to extract the inherent characteristics of panoramic depth images first, and then using this pre-trained model as the teacher model to supervise the student network learning. Now, I will specifically introduce the method we have proposed. In our network, an ERP image serves as an input, and the predict depth is output. The encoder utilizes a context-based pre-trained model to extract features from the input. Similarly, the spherical convolution encoder applies the proposed spherical convolution method to extract distortion-free high-dimensional features of corresponding sizes and channels in shadow networks. Besides, a skip connection structure is applied to enhance the interaction between the encoder and decoder and enrich the high-dimensional information of the image. Following an encoder-decoder architecture, the teacher network takes the ground truth depth image as input. In contrast to conventional depth estimating methods, our framework harnesses the benefits of knowledge distillation networks by employing a teacher network trained with ground truth to extract the inherent characteristics of the depth image. One crucial aspect of performing convolution on a sphere is setting up the appropriate convolution kernel. Different with planar convolutions, convolution on a spherical surface possesses a distinctive characteristic. The kernels, whether rectangular or Gaussian, do not undergo translation, but instead rotation on the sphere. Therefore, the problem of defective rotational invariance of convolution kernels on the sphere cannot be ignored. Our sampling is directly carried out on a sphere, which eliminates the problems of disconnectivity and distortion in contrast to an ERP image representation. Inspired by conventional future point detection, we introduced a circular convolution kernels. Considering that the planar convolutions typically employ 3 times 3 convolutional kernels, we also select 8 equidistant points on the circle, along with the central point as the spherical convolution kernel. Details of the convolution kernel's rotation on the spherical surface and the mathematical derivation can be found in our paper. As shown in the left figure, the proposed spherical convolution kernel takes on different shape in different regions of the image. The future FERP obtained through planar convolution exhibits distortion at the poles, while the future FSPH obtained through the proposed spherical convolution method is distortion-free. In a panoramic image, researchers typically assume significant distortion in the upper and lower thirds, with almost no distortion in the central part. So near the quarter, we hope to leverage the well-established method of planar convolution to effectively extract the future. This strategy enables us to fully harness the benefits of planar convolution in extracting rich features from the image while avoiding the potential adverse impact of spherical convolution in deep layers. To fuse FERP and FSPH, we propose an adaptive weight fusion scheme, where we perform adaptive fusion on the 2 features to obtain an initial fused feature F. The proposed teacher-student network aims to incorporate more depth information into the network by utilizing ground truth depths and to compensate for the shortcomings of spherical convolution in deep layers. The teacher network takes the ground truth depth as input, generating the latent features in the deepest layer, which acts as guidance for the student model. By leveraging the inherent characteristics of teacher model, we can enrich the depth information contained in the latent features of the student model, thereby improving the network's performance in depth estimation. It is important to note that the teacher network is discussed in final inference. During the training process, we employ the commonly used Berhu loss as the loss function for depth estimation tasks. Now is our result. As table shows, our method performs well compared to SOTA methods on several benchmark datasets. It achieves significant performance advantages over several prior methods, including UniFuse, OmniFuse, PanelNet, and HRD Fuse across the Stanford 2D 3D, 3D60, and the Matplotlib 3D datasets. These improvements are evident not only in traditional metrics like absolute relative error and root mean square error, but also in terms of visual quality. In the ablation experiment, we systematically evaluated the effectiveness of each component. Initially, our baseline planar convolution method performed poorly on the Stanford 2D 3D dataset. Subsequently, introducing the spherical convolution method improved the squared relative error by 60.21%. Continuing our optimization efforts, we incorporate the spherical future fusion module, which enhanced the performance by 11.24%. Additionally, integrating the teacher network independently contributed a further 3.3% improvement in squared relative error. Ultimately, Combining all these components led to the maximum improvement of 23% in squared relative error. Besides, we performed evaluation experiments on the weight of SFF module. The experimental results demonstrate that the adaptive weight outperformed the other three fixed weight ratios. Overall, these results clearly illustrate the pivotal roles each component plays in enhancing the overall performance of our depth estimation network. Yes, here is our results. The last one is the thinking. In the final part, we reflect on our future directions. Firstly, we identify the proposed spherical convolution requires offline pre-computation, restricting its adaptability to different image size. This is an area worthy of improvement. Additionally, we aim to implement the proposed model in practical applications, such as visual surveillance, robot navigation assisting in 3D reconstruction, and so on. That concludes the presentation of our work. If you have any question or suggestion for improvement, please feel free to contact our research team via email. Thank you once again for your attention.
Do we have any questions from the audience? Yeah. Okay. You don't. I had one question. How was the ERP and spherical feature adaptive weighting was performed?
And sorry, could you please repeat the question again?
Yeah. So how was the adaptive weighting actually performed in your setup?
You mean the adaptive weighting?
That's right. That's right. Yeah.
You mean the adaptive weighting of the SF module?
Yes. So if you see this slide, so the adaptive weighting when you are merging ERP and spherical features.
Okay. So here we tried many adaptive weighting, but in the panoramic image domain, researchers typically assume significant distortion in upper and the lower thirds, with almost no distortion in the central part. Our method is designed based on this conventional understanding of distortion distribution. Our setting of the weight is based on this principle. Yes.
Okay, thank you.
Thank you very much.
Now we have our third presentation, DQ Horizon Net enhancing door detection accuracy in panoramic images via dynamic quantization.
Morning, everyone. I'm excited to present DQ Horizon Net. Enhancing door detection accuracy in panoramic images via dynamic conversation. I'm the first author, Xinjia Lin from Taiwan National Tsinghua University. My advisor is Hong Guozhu, and this is a joint work with Professor Yao from National Taiwan Technology, National Taiwan University of Science and Technology. So our goal is to perform a door detection in panoramic images. But why panoramic images? Because panoramic images, they carry only vision information, which says that they offer comprehensive viewing. And most importantly, they can preserve the vertical characteristic inside the image, which we found is quite useful in our work. So door detection is a well-studied topic. It can be applied on many applications such as robot navigation or layout estimation. In our discussion today, we will be focusing on two primary categories of approaches. They can be briefly divided into optimization-based approach and learning-based approach. In optimization-based approach, they utilize filters such as Sobol, Kenny, hair, etc. to extract edges and corners. Then they feed this low-level feature into network to get the prediction. In learning-based approach, we can develop a neural network to do this job for us. So we will talk about optimization-based approach first. In this approach, they extract low-level features such as lines, edges, and corners, and then feed it into network like Bayesian network, decision tree, or rule-based model, etc. From this approach, we found something quite interesting is that in this 2014's work, they use rule-based model to detect the top and bottom lines of the wall in the image. And then they use a hair filter to detect the vertical responses. So most of the response to the intensity variance occur near the door frames. This observation inspired us to ask, how can we leverage this characteristic? However, if we naively use these low-level features, we may encounter several issues such as this, including overlapping detection and the misidentification of objects with structures similar to a door. For instance, in this image, the bookshelf is wrongly identified as a door. So we look into learning-based approaches. There are several famous object detection models, such as Spectra CNN, YOLO, and Deter. And as you know, this method uses bounding box annotation. This approach presents certain challenge when dealing with panoramic images. The first significant challenge is the panoramic distortion. As depicted in the image, the panoramic view is distorted. And as you can see the red bounding box, which fails to align accurately with the door's actual corners due to the distortion. This misalignment poses a problem for standard bounding box annotation, as they may not accurately outline the target. Secondly, we encounter the issue of cross-boundary annotation. In the image, there is a door located on the far right. However, due to the distortion inherited in panoramic imaging, it appears torn and displaced to the far left. This characteristic presents a significant challenge to traditional bounding box annotation. Thirdly, the crowded doors. In the image, several doors are positioned near each other. This arrangement could be problematic for traditional bounding box annotation, as it may lead to difficulties in distinguishing each individual doors due to their adjacency. Fourthly, we face the challenge of significant size variance. Due to the distortion in the panoramic images, some doors appear extremely large, while others are markedly small. This discrepancy complicates the use of traditional anchor box method, as it necessitates the preparation of multiple anchor presets in varying sizes, potentially complicating the training process. In summary, We faced several major issues, including the significant distortion, the cross-boundary issues, and the size variance. Traditional bounding box annotation may not provide the accuracy needed for panoramic images and could be inefficient for training purpose. This challenge underscores the necessity for a solution that enhances the accuracy for our annotation in panoramic context. So let's talk about our motivation. Previously, we explored the low-level feature identified in the early work. So can we take a step further to turn it into a high-level feature and utilize them in a deep neural network? So this question put our eyes onto a model called HorizonNet. It takes a panoramic image as input and flattens the vertical information, producing rows of columns, and each column contains 3 values, representing the probability of the corner and the wall to ceiling position and the wall to floor position. However, if we directly adapt HorizonNet for door detection, we will encounter a significant issue, the overproduction of false positives. This problem persists even when we apply a non-maximum suppression. So far, we have outlined the potential challenges. Our key contribution is the development of a method that enables us to adapt HorizonNet for door detection while effectively reducing false positives. This question then arose: how can we transform a dense prediction model like HorizonNet into a sparse prediction model that produces discrete door annotation? So we will talk about it in 4 parts. This is the original HorizonNet architecture. It takes a panoramic image as input and then flatten it into columns of features. We have modified the output of HorizonNet to produce columns of classification alongside with regression output. This modification, along with our custom annotation format, which we will introduce shortly. After applying a maximum filter to the classification logic, we effectively group the values. This step helps us in identifying the peak of the probabilities, which is crucial for isolating the most likely door's location. After identifying the peak columns, we proceed to perform a cost function. This allows us to calculate a cost metric that compares our prediction with the ground truth. By using bipartite matching, we can find a set of least costs within the cost metric. This helps us to pair the prediction with their corresponding ground truth. We call this process dynamic quantization. Now we can talk about our annotation. In a panoramic image, we navigate using 2 axes, the horizontal U-axis and the vertical V-axis. We know the U position of the left side and the right side of the door, so we can calculate the width, which we refer to as delta U. Also, we know the V position of each corner as shown in the image. The U left is determined by the color index, and our regression target consists of these 5 values highlighted in yellow. So let's move to cost function. An image is split into 1,024 columns, and we have a group of columns with unpeak values. Assuming we have ground truth located within a specific column, we can then calculate the distance from other columns to this ground truth, and we call this distance U cost. Our goal is to perform a bipartite matching to identify a set of columns in the cost metric that collectively have the lowest U cost. This enables us to train a model effectively with this paired column. In our experiment, we utilize zero indoor data set to both train and evaluate our model. Our baseline included original HorizonNet and Deter to comparative analyze with our model. It's noteworthy that both of the original HorizonNet and Deter require applying non-maximum suppression to enhance their performance, whereas our model does not. As a quantitative result, our model significantly outperform others, mainly due to our substantial reduction in false positives. This key improvement greatly enhanced the overall precision of our model. As a qualitative result, it is evident that HorizonNet's major issue is the overproduction of the false positives, where deter struggles with accurately detecting those, resulting in a higher rate of false negatives. We can see another cases. So in overall accuracy, our model demonstrates a significant advantage over the baseline, particularly in a scenario where the target door is relatively small. As the door size increased, the original HorizonNet show a comparable performance to our models, where deterred continue to face challenge with distortion and the increased rate of false positives and negatives. In our ablation study, we explore the impact of varying kernel size for the maximum filter on our performance. We observed that the difference in performance between kernel size 29 and 100 is not substantial compared to when the kernel size is set to 0. This indicates that incorporating a maximum filter with a non-zero kernel size does contribute to enhancing the model's accuracy. Here we can clearly see a significant misalignment when the kernel size is set to 0. We also experiment fixing the columns by the same margin. However, if we set the column number too low, it will lack precision, and if we set it too high, it will be similar to the original HorizonNet. Our model does have certain limitations. The primary constraint is that it requires the pitch and roll angles of the camera to fix at 0 degrees, ensuring that the input image are vertically aligned. Another limitation of our model is the requirement for target object to be vertically aligned. This alignment allows us to utilize the color index effectively to pinpoint the object's location. In conclusion, our first contribution is to point out the key challenges in this test. Our key contribution is the introduction of dynamic quantization, which empowers HorizonNet to efficiently perform sparse prediction without the need for post-processing steps like non-maximum suppression. We appreciate the reviewers for their constructive comments and the support from the sponsor, Taiwan National Science and Technology Council. And this is end of my speech. Thank you. Questions? Yes, please.
Thank you, Professor. Often people use CNN, for example, to detect poses of objects.
Yes.
Did you try your baseline to this just to detect the bugs?
Yes, I have seen a paper that is called Indoors 360. That in this paper, they compare the Besra CNN with the regular CNN and the spherical CNN. And in their result, they report that using spherical CNN is not as good as using the normal CNN. So we didn't test the spherical CNN by these papers before. So, okay.
Yeah. Do you think you can extend your work to detect more classes, like so as selling texture like that, or is it too hard due to the
Yes.
girls?
We think our future work, future direction is to extend and loosen our constraint on vertical aligned objects. And there's a work that is doing bidirectional compression. That means they consider not only the vertical compression, but also the horizontal compression. But in their work, they prove that adding the horizontal compression does help to improve the performance, but it's not as effective as vertical compression. So there must be something to maximize the horizontal information, but instead of simply just compress them. Yeah, it's my future work. Yeah. Thank you.
Any more questions? I have one question.
Okay.
So the kernel sizes and the columns ablation that you performed on Zillow Door dataset, do you think that it would vary with datasets? Like this kind of ablation have to be performed every time we pick up a new dataset, or would that not matter?
You mean we have to train the model?
No, like which column, like how many columns give us the best performance? Would that change with dataset, or is it gonna be the same as you said for the?
Oh, now currently 1024 is the output setting by Horizon Net. And I believe that even you extend it with maybe 2000, it will still effectively reduce our maximum filters approach can effectively reduce the training effort to do this. Yeah,
Got it. Thank you.
thank you.
I think our fourth presenter couldn't be here, but they have somebody from their team here to represent for any Q&A. And they have recorded the presentation, so I would like to share.
Hi, Shweta, I can do the presentation. In case it gets interrupted, maybe then you play it. Hi, am I audible?
Yes. You want to play you want to do the recorded version, or you want to present?
I can present, it's fine.
Sure.
Actually, I need to share the screen. I'm not able to share.
No, I think I can do that. Yeah, you can go ahead.
It is actually throwing an error.
Can you see our screen?
Yeah, your screen is visible.
Yeah, I can proceed in the, like, as you proceed, I can move the slides.
Actual format is still showing the media player. Okay, are my slides visible?
Yes, we can see. Uh,
Okay, now is it visible?
I can see. Can you try to change the slide and we can see if it's there?
Yeah, just one second.
Yeah, you can go ahead.
Yeah. So hi everyone. My name is Jaya Bhanushali. I'm a researcher from IIT Madras. And thank you, Praneeth, for sharing the screen, I guess. And this is a collaboration work between IIT Madras and UNC Chapel Hill. So to provide an overview of this work, we propose a technique for cross-domain inference, wherein we train the neural network purely on synthetic omnidirectional scenes. So on the top right corner, you can see that we have basically designed a synthetic omnidirectional data set called OmniHorizon, and we train a neural network on this data set to learn depth and normal information. Once we train this neural network, we take real-world RGB images and infer depth and normal information from these images. So at its core, basically, we propose a data set to train the neural networks in a synthetic domain. And the data set is one of the first contribution. Second contribution is the neural network itself, which learns both depth and normal information in a synthetic domain, but we are able to translate it in a real domain scenario. So to proceed further, first thing I want to discuss is about the prior work. So most of the data sets that are currently available for equirectangular images are indoor data sets, which are either captured from real-world indoor locations or simulated environments. They often represent spaces from different apartment and commercial buildings. Now, these data sets commonly include Matterport 3D, Stanford 2D 3D, Replica 360, Zillow, and Pano 3D. So on the left side, you can see some of the examples from Pano 3D dataset, which was also introduced in OmniCV 2021. So apart from this, on the next slide, you will see an example for outdoor datasets. And one data set that we have found is Fukuoka, which consists of 650 static panorama scans, which consist of high resolution depth and 3D point cloud data, which are captured from various parts of Fukuoka city. Now, this is a little extraordinary data set because it is not perfectly equirectangular. So on the vertical field of view, the data set is around 270 degrees FOV. So one thing we have noticed from both the data sets, either indoor or outdoor, is the scarcity of outdoor omnidirectional data sets, which is also the primary motivation for this work. And obviously, there are multiple challenges in representing these outdoor spaces. For example, sky, time of day settings, and dynamic lighting, which are the factors that are often neglected in the indoor data sets. So we propose Omni Horizon, which is a synthetic omnidirectional data set with 24,335 panoramic views. These images are rendered at 1024 x 512 resolution. The dataset consists of 3 different large scenes which model various aspects of outdoor scenarios. For example, parking lot, public parks, market areas, traffic junctions, roads, and vegetation. And on the right side, you can see the depth distribution for the scenes. So our idea is to basically model the daily activities that are happening in the outdoor scenarios to capture all the dynamic aspects of it. So on the next slide, you'll see about dynamic lighting. So one thing that we have noticed is the geometric information is often independent of lighting conditions. So if something is like 5 meters in front of me, regardless of time of day, let it be midday or it could be golden hours, it is going to be at 5 meters away from me. So ideally, our network prediction should also be independent of the lightning conditions. So in order to ensure that the networks are robust against dynamic conditions, we model these dynamic lightning conditions as a part of our data set. So in the image, you can see that we are modeling one directional light source, which represents sunlight, and a secondary light source, which is skylight, which is ambience in the scene. So by modulating it throughout the different frames and images that are captured throughout the data set, we try to model different time of day settings in the data set in order to ensure that the network learns this kind of shadow and other lightning conditions, sky details. So we also model various sky conditions as a part of this data set. Another important aspect of this data set that we have found, and in fact, it was also mentioned in the one of the first keynote presentations, is the pedestrians. So vehicles and pedestrians are important elements of outdoor scenarios. So for vehicles, we model various classes of vehicles such as trucks, jeeps, SUVs, sport vehicles as a part of our data set. And for pedestrians, we model realistic virtual avatars, which could be pedestrians walking on the street, hanging out in a group, or sitting in a cafeteria. So we try to again model day-to-day life conditions in our data. So this is a comparison chart where we compare Omni Horizon against the existing data sets. As you can see that most of the data sets are indoor data set. The number of panoramic views that we provide are comparable to Panos on CG, but we also provide dynamic scene lighting as well as dynamic components like vehicles and pedestrians, which are often missing in most of the data set. So while introducing a synthetic data cell solves a part of the puzzle, the main aspect of this work was depth and normal estimation from omnidirectional images. Now, UNet is one of the most commonly used architectures for depth estimation. But one thing that we have learned is that UNet generally struggles to estimate normals correctly and often mistakes vertical structures for the ground surface. So in the image, you can see that the input RGB is basically an image of a skating park. So the ground surface and the vertical supporting structures have a very similar texture, because of which the predicted normal does not highlight the vertical structures in the RGB image. And as a result, in the predicted depth also, you can see some of the perturbations that will come in the ground surface. So basically, UNIT is not able to identify these vertical ramps in the skate park. So the question that we learned after a lot of trial and error was like the question of learning the global context. So traditionally, CNNs are based on the convolution operation, which are restricted by the window size in which the convolution is performed. So as a result, for example, if it is being performed on the small ear section of the RGB image for this dog, then the information captured in that specific section basically belongs to the ear area without realizing what is happening in the other parts of the image, for example, the eyes, the nose, and the other ear. So the major breakthrough that was done just few years back was the vision transformers, which used and leveraged the attention mechanism, where you can basically learn first divide the image into multiple tokens and patches and perform attention to learn the relationship at a global context. As a result, we propose UBOTNet architecture, which is a fusion of UNet and bottleneck transformer. So we are still using the UNet transformer to learn the local features using convolutional layers of UNet, but we embed this transformer architecture at the end of the encoder and before the decoder of the unit to learn the global context. Now the bottleneck transformer on the right, you can see the structure basically performs a contraction of the feature space and then performs multi-headed self-attention. And finally, it again expands back the feature to give the D out at 2048. The idea behind the original bottleneck transformer paper is where the authors basically use the transformer network towards the end of a ResNet 50 architecture to improve the predictions. We take a similar inspiration here and embed the bottleneck towards the end of the encoder, which has lowest feature maps. So coming back to the question of learning the global context, by adding the bottleneck transformer to the original unit architecture, we are able to reduce the estimation error and improve the accuracy for normal estimation. So you can see again the same region marked in the image with red square, that when we are performing this prediction with unit and bottleneck transformer, that is UBOTNet, we are able to identify the vertical structures in the bottom right image, where you can see the green and that purple pink color of the structure. And if you look at the depth map and compare it against the vanilla unit architecture, you can see that the depth is much more flat and how the ground surface should have been, rather than having the perturbations in the depth map. So for performing the benchmarks on Omni Horizon, these are our training configuration parameters. And we use 3 total augmentation techniques, out of which 2 techniques augment the color data. They perform channel shuffle and color jitter. And we use a third technique for random rotation on the image. And these are our loss functions, where we perform a joint learning of depth and normal information from input monocular omnidirectional images. So for loss objective for depth estimation, we use the reverse Hobart function, also known as Beru. And for estimating the scene normals, we use L1 penalty. So the overall loss function is calculated as a sum of loss for depth error and loss for normal error. And these are our results on the benchmark on Omni Horizon. We tried to cover most of the state-of-art architectures for this benchmark. And from the quantitative results, you can see that UBOTnet generally performs around 14.92% better than UNet for normal error and 4.45% for normal accuracy. We also see improvements in depth accuracy compared to the original UNet architecture. And other than this, our emphasis was not to introduce a new architecture to beat other state-of-art architectures, but like I mentioned, we wanted to solve the issue with normal estimation. So these are the qualitative results on the Omni Horizon dataset. Like you can see in the middle row for UNet, the normal estimation suffers for the RGB image because it is nowhere close to the ground truth. Whereas if you see the results from the UBOTnet architecture, they are pretty much closer to the ground truth compared to any other existing architectures. Now to bring a real world example, we take the scenario for sim to real transfer, where we pre-train the UBOTnet on Omni Horizon and then fine-tune it on Fukuoka for task of depth estimation. We also compare it against training UBOTnet from scratch on Fukuoka. Totally, we trained for 80 epochs for both the scenarios. So in the first scenario on the right image, you can see the no pre-training context, and on the towards second column, you can see the pre-trained on Omni Horizon. So overall, we observe that the depth accuracy sees a significant boost when you pre-train the data set on Omni Horizon. And to bring back the context, Omni Horizon is a synthetic data set, whereas Fukuoka is a real world data set. So still you can see that we can leverage by training it on a synthetic data set and improve our results. And these are the output for prediction on real world images captured in the wild. So what we do is we take random images from the internet and we try to identify how the depth and normal estimation was performed by UBOTnet after training purely on Omni Horizon. So you can see that we take scenarios of urban buildings, public parks, complex building structures, and different dynamic lighting conditions. In the first row, you can see that the building structure as well as park are correctly identified in terms of normal estimation as well as depth data. In the third row, you can see the very overexposed lighting condition, which is still covered very well in the context of normal estimation and depth estimation. The second set of examples are towards vegetation, because vegetation is one context which I generally found missing in a lot of data sets. So we wanted to see how it tackles using a synthetic data set. So the first row is basically a very close-up picture of a tree, whereas second row is a forest area picture, and third row is a park picture with trees and stairs. As you can see that in all the contexts, even if the tree is near or you're looking at a forest, or in the third scenario, it is a park with stairs. In almost all the contexts, the network predictions are consistent. There are several limitations to our work. First, we found that the network fails to estimate depth and normal in scenarios with overexposed regions because these images are captured in the wild. So there are certain images where there could be overexposure due to the sunlight. So in those scenarios, the network will fail to basically identify depth and normal for that specific region. And there are certain scenarios where it will fail to identify certain vertical upright structures, such as bridge railing, as you can see in the second image, which has been highlighted with red mark. And these are examples where basically in that there's actually water behind that bridge. So this makes it a complex scenario where you have water involved, there's a bridge rail, and there are trees in the back. So for conclusion and future endeavors, we hope that this data set will improve the general understanding of outdoor scenarios from omnidirectional images. We also aim to increase the immersion for virtual reality. So our background, basically the background of our lab is in virtual reality and haptics. So this was like our first working towards immersion in VR, which is the application we are currently exploring. And our lab also is working towards robots. So we are seeing how this kind of work can be used to improve the scene navigation for robots using omnidirectional image. Thank you.
Okay, I had one question. I think in a table you have mentioned about unit bot light.
Yes.
So how is that different than U-botnet?
I have not covered it in slides here, but UBotnet Lite is basically using separable convolution layers, which allows us to compress the number of parameters that the network is using. So we are able to compress it by like 70% without sacrificing too much on performance. So one of the things like that we were testing was to perform this with real world 360 videos rather than images. So by having a network which is not very large, we can do it close to real-time performance, like close to 15 frames per second. Apart from that, like it is very identical to the original architecture. So separable convolutions is a trick people use to compress the number of parameters in a CNN architecture.